There's a lot related between what we did in 6.2 and 6.3. And so this slide, you can write down at the end or take a picture at the end, but it's not important in terms of what you're going to do. It's just sort of an explanation of why it changes a little bit. And then we talk about what the central limit theorem actually is. So here's the thing. In 6.2, the problems that we did, and I know it's been a long time, where we had problems where we had some boundaries, lower and upper boundaries. We had the mean and we had the standard deviation. And then we did that normal CDF in our calculator, and it would tell us the percentage or the decimal that was in that area. The thing with 6.2 is we assumed that it was the entire population. Bless you. Okay? And for 6.3, that's not going to happen. Okay? In 6.3, we're going to be talking about just a sample. And when we have a sample, we have to make an adjustment to our standard deviation.
Wait, what lesson are we on?
6.3. Okay?
What are we next Monday?
So when we deal with the sample, our calculations and properties have to change a little bit, but not very much. And I'm just going to kind of walk you through that. So here are the properties, okay? And this is on 331 if you want to screenshot it from your book. But here's where the properties change a little bit. The first part actually doesn't change at all. The mean of the sample means is going to be the same as the mean from the population, okay? So the means aren't going to change. That's what this is saying. When you have the mean for the sample, you will use that mean in the exact same way that you used it in 6.2 as if it was a population. So that part doesn't change. It's the next thing after that where there's a change. And it's going to be super wordy.
Oh, yeah.
But you don't have to know all the words. It's more of an explanation getting to the place where we want to. So this is, and I'm going to show you the math for what that's saying down below. But essentially what it's saying is that in a sample, the standard deviation has to be a little bit smaller than the standard deviation of the population. Okay? And all you have to do to make it a little bit smaller is you take the standard deviation and you divide it by the square root of the sample size. And that makes the standard deviation a little smaller. And that's what we will use in place of standard deviation. Okay? So get that in your notes, and then I'll show you what the math looks like that goes with it. This is what it's saying. Okay? So Are
you recording?
The standard deviation of the sample mean is also known as the standard error of the mean. And so all we do is we take that standard deviation divided by the square root of the sample size. And just to line all up, okay, so what's in red? Standard deviation of the sample mean. That's what this means, this subscript x with the bar, that means mean. So the standard deviation of the mean.
Oh. Are we worth
Okay, and the standard deviation divided by the square root of the sample size. So again, this standard deviation for the sample means is also known as the standard error of the mean, because we're accounting for the fact that since we are only using a sample instead of the entire population, that there is some error built into it, margin for error built into it. The only thing that has to be done when you're dealing with the sample is this adjustment. And you divide the standard deviation by the square root of n, the square root of sample size, and everything else is the same. Okay, now that being said, we get into what's called the central limit theorem. And here's what the central limit theorem is about. It's about really the shape of the curve, the shape of the distribution. And as the sample size increases, the shape of the distribution will go closer and closer to a normal distribution. Okay? Which means we're going to be able to use the same math that we used before to do some of these problems. And it's going to look like this. Okay? So everything's the same here as what we've done before, except we have to make the adjustment with the standard deviation. Okay? And actually this should technically be x with the bar on it, because mu is the mean for the population. but I didn't want to change it just because you're gonna pull the mean, and whether you use mu or you use x with the bar on it, you're gonna use the mean. It doesn't matter, they're the same. And that's what we said on the previous page, that the sample mean and the population mean for the purposes of doing these problems are the same number, so they can be used interchangeably.
Which are the two same?
So all this is exactly the same as what we did except for the standard deviation over here. So you're going to want to be careful when you enter this into your calculator. You're going to want to put this whole fraction in parentheses for the standard deviation line. Bless you. Okay, so you're still going to, when you do the normal CDF and you enter it in on your sort of listing there, you're going to enter what the standard deviation is into the standard deviation slot. You're just going to have to write it as a parenthesis. So here's the problem. Go ahead and take a picture of that, and then we'll work through it. Now, one of the things that's going to happen in these problems is it's not necessarily going to explicitly say whether it's a sample or a population. Most of the time, you're going to have to figure that out from the context of the problem. Okay? And in this problem, we're talking about some type of dexterity test for 12-year-olds, and the mean score is 30. We don't know what the scoring is based off of or anything like that, and it's not important. The standard deviation is 5. The psychologist is going to administer the test to a class of 22. Okay, so 22 is the size of the sample. Keep in mind that what we need to do is we're going to use this formula, and it's in your calculator. So again, if you can enter it in your calculator, remember how to get there, second bars in the distribution menu.
What do you put for mu?
Okay, so good question.
30.
Right, the mean is 30. So the population mean and the sample mean are the same thing. Here's where you have to make your adjustment. Just make sure, like I said, you probably want to put all of this into its own set of parentheses. If you can, I don't know if it'll let you turn, put a fraction in that spot. If not, you'll just have to put it in as a division problem. What is n for this problem? 22. The number of students in the sample is 22, so n is 22. Okay, here's what it should look like.
So what did your answer get?
Okay, so when you enter this in your calculator, after you hit enter or paste, I guess, this is what you should get on the next screen. Now it might express this part a little bit differently. Like I said, that's that whole fraction division thing. Anybody having any issues getting that entered in their calculator? Oh, and actually, hold on one second. One thing I don't want you to do, okay? I do not want you to plug the square root of 22 in your calculator, then estimate some decimal there. I want you to enter it in exactly like this. Okay, the only other thing that you could do, if necessary, is write it as a division problem. Okay, but don't actually make a decimal out of it. Let the calculator take the exact value, because then it'll give you a more accurate answer. Okay. Okay. So, how many had this for their answer?
I did.
Okay. And at this point, either one is fine. I guess, again, probability. Most of the time when we talk about probability, we talk about it as a percentage versus a decimal. But either one's fine unless it tells you they want it a certain way. Okay? Are there any questions about that? All right. Let's do some more. Here's another one. Take a picture of that and do it. Yeah, there's going to be some positive infinity going on here. Yeah. But in reality, it's still really not that much different. Okay?
Okay, so your lower would be 42.
Correct. Here's my setup if you want to check and see if you got the same thing.
That's when you do the one.
Yep. Here's what you should have gotten.
You're wrong, but
How many got it?
hey, I got them.
All right, good. Okay, we got a couple more to do. And they're on the same page. Okay? And go ahead and take a picture of that. And then if you want to work through both of them and do both of them, that's fine. It's the same example, the situation probability that you're finding is a little bit different from A to B, but it's still based off the same example. So do those two, and then we're going to talk about it a little bit. On this first example, what's important to see, and I'm going to point out here in a second, is that the sample size is how big for A?
One.
A single egg, okay? Which means what happens is, when you look over here, the square root of 1 is what?
One.
So 15 divided by 1 is? So this situation, it's not 1, it's 15. Nice try. So this ends up being the same as 6-2. When the sample size is only 1, the calculation is exactly the same as if it was the entire population. Okay? Which also means, if you want to do some analysis on it, which you may or may not have to do, it's trying to tell you that your sample size is so small that it's not necessarily reliable, so your margin for error would be much greater. Anyway, so that's what you should have gotten, but in all reality, just keep in mind that this is the same as just 15. Okay, so when you have a sample size of 1, you can leave the square root of 1 out, just because it doesn't change the value. Okay, how many had that for your answer? All right. Now on part B, the only thing that changes the sample size is 25 now instead of 1. Everything else stays the same, and you should get that. Okay? Questions about any of this?